99% of the universe is already dead to us, forever unreachable no matter what we invent. Everything you've been told about space exploration is a lie. We can't go to the stars. Physics won't let us. Today, we're exploring the absolute limit of human travel through space, the cosmic boundary that separates the reachable from the forever unreachable. And here is a question for you. If you could break one law of physics for a day, which would it be? And what would you do? Let me know in the comments. I will pin the most creative answer. Now let's begin. We are living in a universe that's not just big, it's incomprehensibly vast. When we look up at the stars, we're seeing light that has traveled for years, sometimes millions or billions of years, just to reach our eyes. Every photon carries a story from the distant past. But here's something that will change how you think about space exploration forever. There are galaxies out there right now whose light is reaching us at this very moment, but we could never reach them. Not in a million years, not in a trillion years, not ever. Even if we left today, traveling at nearly the speed of light, we would never arrive. The universe has placed fundamental boundaries on how far we can go. These aren't just technological limits. These are walls built by the very fabric of space and time itself. Let me tell you about the first spacecraft humanity ever sent beyond our solar system. In 1977, NASA launched Voyager 1. This probe, about the size of a small car, was designed to study Jupiter and Saturn. But after completing its primary mission, something remarkable happened. It just kept going. Voyager 1 became our first ambassador to interstellar space. As of 2026, 49 years after launch, this incredible machine has traveled more than 24 billion kilometers from Earth. That's roughly 160 times the distance between Earth and the Sun. It's now so far away that a radio signal traveling at the speed of light takes about 22 hours to reach it. 22 hours for light itself. Here's the mind-bending part. After nearly half a century of continuous travel, after crossing into interstellar space, after leaving behind everything we've ever called home, Voyager 1 has traveled approximately 0.0025 light years, not even 3,000ths of a single light year. The nearest star system to us, Alpha Centauri, is 4.37 light years away. At Voyager's current speed, it would take about 73,000 years to get there. 73,000 years. Think about that. When Voyager was launched, humans were just beginning to use personal computers. The internet didn't exist. Now imagine waiting 73,000 years. When Voyager would finally arrive at Alpha Centauri, assuming it were headed there, which it isn't, our entire civilization would have risen and fallen countless times. New ice ages would have come and gone. The constellations themselves would look different because the stars move relative to each other over such vast time scales. And here's what keeps me up at night. Alpha Centauri is our closest stellar neighbor. It's in our cosmic backyard, yet it's so far away that our fastest probe would take longer to reach it than humans have existed as a species. Now, if you're starting to feel small, don't worry, we're just getting started, because the real mystery isn't just how far away things are, it's about what's happening to space itself while we try to cross it. You see, the universe isn't static. It's not a frozen stage where objects simply sit in place. Space itself is stretching, expanding, growing larger with every passing second. And this expansion changes everything about what we can and cannot reach. In 1929, an astronomer named Edwin Hubble made a discovery that revolutionized our understanding of the cosmos. He observed that distant galaxies weren't just moving through space, they were receding from us. The farther away a galaxy was, the faster it appeared to be moving away. But here's the crucial insight. These galaxies weren't moving through space like cars on a highway. Space itself was expanding, carrying the galaxies along with it. Imagine the universe as a balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart, not because they're racing across the rubber, but because the rubber itself is stretching. That's what's happening to space. Now you might think, so what? If space is expanding, we'll just need faster spaceships, build better rockets, more powerful engines, travel faster. Problem solved, right? Wrong. Because the expansion of space follows rules that shatter our intuitive understanding of distance and speed. The rate of expansion is described by something called the Hubble constant. Recent measurements from missions like the Dark Energy Survey and observations from the James Webb Space Telescope have refined our understanding of this value. As of 2024, the best measurements suggest the universe is expanding at roughly 70 kilometers per second per megaparsec. Let me translate that into something we can grasp. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years you move away from us, space is stretching such that distant objects appear to recede an additional 70 kilometers per second. Here's where it gets wild. Close galaxies, the ones in our local group like Andromeda, aren't really affected by this expansion. Gravity holds us together. But go far enough out and you reach a point where the expansion of space between us and a distant galaxy is happening faster than the speed of light. Yes, you heard that right. Faster than light. Now, before you say, wait, I thought nothing could travel faster than light, you're correct. But there's a loophole. Objects cannot move through space faster than light. That's a bedrock principle of Einstein's special relativity. But space itself isn't an object. Space can expand at any rate whatsoever. There's no speed limit on the stretching of space itself. This means there are regions of the universe that are receding from us faster than light. And if space between us and those regions is stretching faster than light can cross it, then light from those places can never reach us, ever. This boundary, this cosmic horizon beyond which light cannot reach us, is called the cosmological horizon. Currently, based on our best understanding of dark energy and the expansion rate, this horizon sits at roughly 46.5 billion light-years away. But wait, you might be thinking, if the universe is only about 13.8 billion years old, how can there be anything 46.5 billion light-years away? Shouldn't the most distant thing we can see be 13.8 billion light-years away, since that's how long light has had to travel? That's an excellent question. The answer is expansion again. Light from those distant objects has been traveling toward us for nearly 13.8 billion years. But during that time, space between us and those objects has been expanding. So while the light has been on its journey for 13.8 billion years, the object that emitted that light is now much farther away than 13.8 billion light-years. In fact, it's now about 46.5 billion light-years away. This is why the observable universe, the sphere of space from which light has had time to reach us, has a radius of 46.5 billion light-years, not 13.8 billion light-years. If you're finding this fascinating, do me a favor and hit that subscribe button. Trust me, there's so much more mind-blowing stuff coming. Every week, we explore the deepest questions about our universe. Don't miss out. Now here's the existential kicker. The observable universe is not the same as the reachable universe. Just because we can see something doesn't mean we can ever get to it. In fact, most of what we can see right now, today, is already unreachable, forever beyond our grasp. No matter how advanced our technology becomes, to understand why, we need to talk about something mysterious and unsettling, something that makes up nearly 70% of the universe, yet we have no idea what it actually is. It's called dark energy. In 1998, two independent teams of astronomers made a discovery that shocked the scientific world. They were studying distant supernovae, stellar explosions so bright they can be seen across billions of light-years. These particular supernovae, called Type E supernovae, are incredibly useful because they always explode with roughly the same brightness. This makes them excellent cosmic distance markers. By measuring how bright they appear from Earth, we can calculate how far away they are. The teams expected to find that the expansion of the universe was slowing down, gradually decelerated by the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The universe's expansion wasn't slowing, it was accelerating, speeding up. Something was pushing space apart faster and faster. This mysterious force is what we now call dark energy. We don't know what it is. We can't see it, we can't touch it, but we can measure its effects, and those effects are profound. Dark energy is driving galaxies apart at an ever-increasing rate. The farther away something is, the faster it's accelerating away from us. This acceleration has a devastating consequence for the future of space exploration. There's a sphere around Earth, a boundary in space, beyond which galaxies are receding so fast that even light cannot make the return journey. This boundary is called the cosmic event horizon, and it's shrinking. Currently, the cosmic event horizon sits at roughly 16.5 billion light-years away. Any galaxy beyond this distance is receding so fast that even if we sent a light-speed signal toward it today, that signal would never reach it. The space between us would expand faster than the signal could cross it. The light would spend eternity chasing a destination that keeps slipping farther away. It's like running on a treadmill that keeps speeding up. No matter how fast you run, you can't make progress. For galaxies beyond the event horizon, we are not just separated by distance, we are causally disconnected. We exist in separate, non-overlapping portions of space-time. Nothing we do can ever affect them. Nothing they do can ever affect us. Now here's what terrifies and amazes me in equal measure. The event horizon is getting closer. As dark energy continues to accelerate the expansion of the universe, more and more galaxies are crossing this boundary, disappearing from our reachable universe forever. Every day, thousands of galaxies slip beyond our cosmic reach, and once they cross that line, they're gone. Not just practically gone, fundamentally, permanently, irreversibly gone. Let that sink in. The universe we can potentially explore is shrinking. The pool of stars, planets, and galaxies we might one day visit is evaporating. Tick-tock, tick-tock. The clock is running, and it cannot be stopped. But let's pause for a moment and ask the obvious question. Why are we limited to thinking about this in terms of conventional travel? Why can't we just build faster spaceships? After all, humanity has a proud history of breaking through seemingly impossible barriers. We went from the first powered flight to landing on the moon in just 66 years. We've built particle accelerators that smash atoms together at 99.9999% the speed of light. Surely, with enough time and ingenuity, we could build a starship that travels at a significant fraction of light speed, right? The answer is yes, but with massive caveats. Let's explore what it would actually take to travel between the stars at relativistic speeds. And trust me, when you understand the engineering challenges involved, you'll see why even our wildest dreams face fundamental physical limits. First, we need to talk about propulsion. Getting a spacecraft up to high speeds requires energy, a tremendous amount of energy. The relationship between speed and energy isn't linear, it's exponential. Moving at twice the speed doesn't require twice the energy. It requires far, far more. Chemical rockets, the kind we've been using since the dawn of the space age, are hopelessly inadequate for interstellar travel. The Voyager probes, our fastest conventional spacecraft, travel at about 17 kilometers per second. That's incredibly fast by everyday standards, roughly 50,000 kilometers per hour. But in cosmic terms, it's glacially slow, barely 0.006% the speed of light. To reach even 10% light speed using chemical rockets would require more fuel than exists in several planets. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, shows us why. The amount of fuel needed increases exponentially with desired speed. At some point, you need so much fuel that the fuel itself becomes too heavy to accelerate. You hit a wall. So what are the alternatives? Nuclear propulsion offers more promise. Instead of chemical reactions, you harness the energy from nuclear fission or fusion. These reactions release millions of times more energy per unit mass than chemical fuels. Concepts like nuclear pulse propulsion, where you literally detonate nuclear bombs behind your spacecraft and ride the shockwave, could theoretically reach 5 to 10% of light speed. The most famous design, Project Orion, was studied seriously by NASA in the 1950s and 60s. Engineers calculated that a massive Orion spacecraft could reach Alpha Centauri in roughly 130 years. Still a multi-generational journey, but at least within the realm of human timescales. Then there's fusion propulsion. If we could master controlled nuclear fusion, the same process that powers the Sun, we could theoretically achieve even higher speeds. Various designs for fusion rockets have been proposed over the decades. The British Interplanetary Society's Project Daedalus, conceived in the 1970s, envisioned a two-stage fusion rocket that could reach 12% light speed, arriving at Barnard's star 6 light-years away in about 50 years. More recent concepts like Project Icarus, an update to Daedalus, suggest similar possibilities. But here's the problem. We still haven't achieved sustained net positive fusion energy here on Earth, let alone in a compact rocket engine traveling through the void of space. What about more exotic propulsion systems? This is where things get really interesting. One concept that's received serious scientific attention is the laser sail, sometimes called a light sail. The idea is beautifully simple. Instead of carrying your fuel with you, you leave the power source at home. A massive laser array, perhaps built on Earth or in orbit, fires an incredibly powerful beam at a tiny spacecraft equipped with a reflective sail. The photons from the laser push against the sail, gradually accelerating the craft. Because the spacecraft doesn't need to carry fuel, it can be extremely lightweight. And because you can keep firing the laser for months or even years, you can accelerate to tremendous speeds. This isn't science fiction. The Breakthrough Starshot initiative, announced in 2016 by billionaire Yuri Milner, along with physicist Stephen Hawking, proposed exactly this approach. The concept called for thousands of gram-scale spacecraft, each equipped with a lightweight sail, to be accelerated by a 100-gigawatt ground-based laser array. The goal? 20% of light speed. At that velocity, these tiny probes, called star chips, could reach Alpha Centauri in about 20 years. Once there, they'd spend just minutes flying through the system, gathering data and beaming it back to Earth. The signal would take another 4.37 years to arrive, meaning we'd get our first close-up images of another star system roughly 25 years after launch. It's an audacious vision, and on paper the physics checks out. But the engineering challenges are staggering. Building a 100-gigawatt laser requires technology we simply don't have yet. For reference, that's roughly the output of 100 nuclear power plants, all focused into a coherent beam. The sail would need to be incredibly thin, just atoms thick in places, yet strong enough to withstand the intense laser bombardment without vaporizing. The targeting system would need to be accurate enough to hit a sail the size of a small room from Earth, even as it accelerates to relativistic speeds. And perhaps most daunting, the entire probe would need to be miniaturized to the point where cameras, computers, power systems, and transmitters all fit into something weighing just a few grams. Speaking of the challenges of interstellar travel, if you want to dive deeper into the massive obstacles we face when trying to journey between stars, check out my video called "The Big Problem with Interstellar Travel Nobody Talks About." I break down some of the hidden dangers and engineering nightmares that most people don't even consider. It'll blow your mind. The link is in the description. Now, even if we solve all these problems, even if we build laser sails or fusion rockets or some technology we haven't even imagined yet, we still face the ultimate speed limit, the speed of light. 300,000 kilometers per second, approximately 1 billion kilometers per hour. This isn't just fast. It's the maximum speed at which information, matter, or energy can propagate through space. Einstein's special relativity, published in 1905, revealed that the speed of light is absolute. It's the same for all observers, regardless of their own motion. And crucially, nothing with mass can ever reach it. Here's why. As an object accelerates closer and closer to light speed, its mass effectively increases. This isn't just a mathematical trick, it's a real physical effect. The faster you go, the more energy is required to accelerate you further. At 90% light speed, you'd need roughly twice as much energy to accelerate a given amount compared to when you were at rest. At 99% light speed, you'd need about 7 times as much. At 99.9%, over 22 times. The curve approaches infinity. To actually reach 100% light speed would require infinite energy, which is, by definition, impossible. But let's say we get close. Let's imagine a future civilization that has mastered near light speed travel. They've built ships that can cruise at 99.9% of light speed. Even at this incredible velocity, something remarkable happens. Time dilation. This is another consequence of special relativity. As you approach light speed, time for you, aboard the spacecraft, slows down relative to the outside universe. This isn't an illusion or a trick of perception. Time actually passes more slowly for you. An observer on Earth would measure your journey to a star 10 light-years away as taking just slightly over 10 years. But for you, aboard the spacecraft, subjective time passes much more slowly. At 99.9% light speed, that 10-year journey would feel like only about 5 months. This creates a strange asymmetry. You could, in principle, travel to very distant parts of the universe within a human lifetime, at least from your own perspective. You'd experience the journey as taking years or decades. But when you arrived, centuries or millennia would have passed on Earth. Everyone you knew would be long dead. Civilizations would have risen and fallen. You'd be a time traveler moving forward through time without the possibility of return. This is the relativistic rocket paradox. You can go far, but you can never truly go home, and even this has limits. Remember the cosmic event horizon? That boundary, currently about 16.5 billion light-years away, beyond which galaxies are receding too fast for even light to reach? Well, that sets an absolute limit on where you can go, even with a near-light-speed spacecraft. You might think, if I travel at 99.999% of light speed, couldn't I just keep going forever, using time dilation to compress the subjective journey? The answer is no, because while you're traveling, the universe continues to expand. Dark energy continues to accelerate that expansion. Galaxies continue to slip beyond the event horizon. A landmark paper by cosmologist Lawrence Krauss and physicist Robert Scherer, published in 2007, calculated exactly how much of the universe remains accessible to a hypothetical civilization with unlimited technology and unlimited time. Their conclusion? Only about 3% of the galaxies we can currently observe will ever be reachable, even if we left today at near light speed. 3%. That means 97% of the galaxies whose light is reaching our telescopes right now, whose images we can see and study, are already forever beyond our reach. The distance to them is growing faster than we could ever cross it. Even riding a beam of light itself, we'd be like Achilles chasing the tortoise in Zeno's paradox, forever running, but never catching up. Let's talk numbers. Our local group of galaxies, which includes the Milky Way, Andromeda, Triangulum, and about 50 smaller dwarf galaxies, is gravitationally bound. Gravity overcomes the expansion of space at this scale, so everything in the local group will remain accessible indefinitely. Beyond our local group, we have the Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. Some estimates suggest that portions of the Virgo supercluster might still be reachable, but only if we act relatively soon on cosmic timescales. Within several billion years, expansion will have carried even these neighboring structures beyond reach. The really sobering calculation comes when you look at the total number of galaxies in the observable universe. Current estimates suggest there are approximately 2 trillion galaxies within our cosmic horizon. 2 trillion, each containing hundreds of billions of stars, each of those stars potentially hosting planets. But of those 2 trillion galaxies, only about 100 billion reside within the volume of space that we could ever reach, even in principle. That's 5%. 95% of all the galaxies in the observable universe are off limits forever. And it gets worse. That 5%, it's shrinking. Every moment, more galaxies cross the boundary from reachable to unreachable. The pool of potential destinations is evaporating before our eyes. If a future civilization wanted to embark on a grand project of exploring the cosmos, settling distant galaxies, spreading life throughout the universe, they're running out of time. Not human time, cosmic time. Every billion years that pass, the reachable universe shrinks further. Eventually, in the deep future, trillions of years from now, only the local group will remain. Everything beyond that will have receded into darkness, invisible and unreachable, separated from us not just by distance, but by the fundamental structure of space-time itself. Now, I know what some of you are thinking. What about wormholes? What about warp drives? What about all those exotic concepts from science fiction that allow faster-than-light travel without actually breaking the light-speed barrier? These are legitimate questions, and they deserve serious answers. Because here's the thing, some of these ideas aren't just fantasy, they're grounded in real physics. But as we'll see, the universe has a way of closing loopholes just when they seem most promising. Let's start with wormholes. The concept comes straight from Einstein's general theory of relativity, published in 1915. General relativity describes gravity not as a force, but as a curvature of space-time. Massive objects like stars and planets bend the fabric of space around them, and other objects follow the curves in that fabric. Now, the equations of general relativity allow for some truly bizarre solutions. One of these solutions, first discovered by physicist Ludwig Flamm in 1916, and later popularized by Albert Einstein and Nathan Rosen in 1935, describes what we now call a wormhole. Imagine space-time as a two-dimensional sheet. Now imagine folding that sheet so 2 distant points come close together. A wormhole would be like a tunnel connecting those 2 points, allowing you to travel between them without traversing the vast distance across the surface of the sheet. In 3-dimensional space, a wormhole would connect 2 regions that might be billions of light-years apart through a shortcut that could be just meters long. Step through one end, and you instantly emerge from the other, having crossed cosmic distances in a single step. It's a beautiful idea. And mathematically, it's allowed by the equations of general relativity. But here's the catch. Every solution for a stable, traversable wormhole requires something called exotic matter, not antimatter, which we've created in laboratories, not dark matter, which we've detected through gravitational effects. Exotic matter. This is a hypothetical form of matter with negative energy density. In simpler terms, it would have negative mass. It would fall up instead of down. It would push instead of pull. And as far as we know, it doesn't exist. We've never observed anything with negative mass. Some quantum field effects can create tiny regions with negative energy density, like the Casimir effect, where 2 metal plates placed extremely close together in a vacuum experience a strange, attractive force. But these effects are minuscule, operating at quantum scales. Scaling them up to create a macroscopic wormhole would require amounts of exotic matter that might simply be impossible to produce. Even if exotic matter exists, and even if we could somehow gather enough of it to construct a wormhole, we face another problem. Wormholes, according to our best calculations, are catastrophically unstable. Any slight perturbation, even a single photon passing through, could cause the wormhole to collapse in on itself. Some physicists have proposed that a sufficiently advanced civilization might be able to stabilize a wormhole using exotic matter and precise control of quantum fields, but this ventures into the realm of pure speculation. We're not just talking about technology we don't have. We're talking about technology that might violate fundamental laws of physics. And even if, in some miraculous future, we could create and stabilize a wormhole, there's another limitation that's rarely mentioned. You can't use a wormhole to travel to a place you haven't already been. Here's why. To create a wormhole connecting Earth to, say, a planet orbiting a star in the Andromeda galaxy, you'd first need to transport one end of the wormhole to that planet. And to do that, you'd need to use conventional transportation, traveling at sublight speeds, subject to all the limitations we've already discussed. So wormholes, even if they're possible, don't solve the fundamental problem. They could shorten travel times once established, but establishing them in the first place requires conventional travel. What about warp drives? This is another concept that emerges from general relativity, but with a different twist. In 1994, physicist Miguel Alcubierre published a paper describing what's now called the Alcubierre drive. The idea is ingenious. Instead of moving through space, you move space itself. The warp drive would contract space in front of the spacecraft and expand it behind, creating a bubble of flat space-time around the ship. The ship itself wouldn't be moving through space at all. It would be carried along by the expansion and contraction of space around it. Because the ship isn't moving through space, it doesn't violate the light speed limit. In theory, there's no limit to how fast this bubble of space could move. It's essentially surfing on a wave of space-time. And mathematically, it works. The equations hold up. But once again, we run into the exotic matter problem. The Alcubierre drive requires enormous amounts of negative energy to create the space-time distortion. Early calculations suggested you'd need a mass energy equivalent to the entire observable universe, converted into exotic matter with negative mass. More recent refinements have brought that number down, but even the most optimistic estimates still require exotic matter in quantities we have no idea how to produce. There are other problems too. A paper published in 2012 by physicists at the University of Sydney showed that as a warp bubble accelerates, it would accumulate high-energy particles on its leading edge. When the bubble finally decelerates and releases these particles, they'd be emitted as a catastrophic burst of radiation that would incinerate anything in front of the ship, including your destination. So even if you could build a warp drive, using it might destroy whatever you're trying to reach. Another study suggested that the interior of a warp bubble might not be causally connected to the exterior, meaning you couldn't actually steer the ship or turn it off once it's activated. You'd be trapped inside a runaway bubble of space-time with no way to control where you're going. And perhaps most fundamentally, there's a theorem in general relativity, proven by physicists Stephen Hawking and others, showing that any mechanism that allows faster-than-light travel also allows time travel into the past. This creates causality violations, paradoxes. The famous grandfather paradox, where you go back in time and prevent your own birth. Most physicists believe the universe must have some mechanism to prevent such paradoxes, and that mechanism likely involves making faster-than-light travel impossible. The universe protects its own consistency. So where does this leave us? If conventional propulsion hits the light speed limit, and exotic solutions like wormholes and warp drives require physics we don't understand and materials we can't create, are we truly trapped? Is the cosmic horizon an impenetrable barrier? The honest answer is, based on everything we currently understand about physics, yes. The observable universe is vast, containing trillions of galaxies, but the reachable universe is a tiny fraction of that, and it's shrinking. But let's zoom out for a moment. Let's think about this from a different perspective. What does it mean to travel somewhere? What does it mean to explore the universe? Must we physically visit every galaxy, every star, every planet? Or are there other ways to extend our reach across the cosmos? This is where the conversation gets really interesting, because it forces us to think not just about technology, but about what we are and what we could become. Consider this. Right now, at this very moment, you are made of atoms. Carbon, hydrogen, oxygen, nitrogen, and traces of dozens of other elements. These atoms were forged in the cores of ancient stars, scattered into space when those stars exploded as supernovae and eventually coalesced into the molecular clouds that birthed our sun and solar system. You are literally made of stardust. The iron in your blood, the calcium in your bones, the oxygen you breathe with every breath, all of it came from stars. In a very real sense, you are the universe experiencing itself. You are a way for the cosmos to know itself. Now imagine a future where we've mastered biotechnology and artificial intelligence to the point where we can encode the essence of who we are, our memories, our personalities, our consciousness, into information, pure data. That information could be transmitted at light speed, riding on laser beams or radio waves across the cosmos. You could, in principle, transmit yourself to a distant star system. Upon arrival, the signal could be used to reconstruct you, whether in a biological body grown from local materials, a synthetic form, or perhaps something we can't even imagine yet. The you that arrives would have your memories, your thoughts, your sense of self. Is that travel? Is that you? These are profound philosophical questions, but they open up possibilities that physical travel does not. Even without such advanced technology, we already extend our reach through robotic explorers. The Voyager probes carry a piece of humanity into the cosmos. The rovers on Mars are our eyes and hands on another world. The Hubble Space Telescope and the James Webb Space Telescope allow us to see galaxies billions of light years away, observing the universe in wavelengths our eyes could never perceive. In a sense, we've already visited those distant realms. We've gathered their light, analyzed their composition, studied their structure. We know what elements they contain, how fast they're moving, how old they are. We've touched them with our technology and our minds, even if we've never set foot there. And this points to a deeper truth. The purpose of exploration isn't just to plant flags, it's to understand, to learn, to expand the boundaries of knowledge. Every photon that reaches Earth from a distant galaxy carries information. The wavelength tells us about the galaxy's motion. The spectrum tells us what elements are present. The intensity tells us how far away it is. By studying these messengers of light, we're engaging in a form of cosmic archaeology, piecing together the story of the universe from the clues written in starlight. In this sense, the universe is already accessible to us, not through travel, but through observation. The James Webb Space Telescope, launched on Christmas Day 2021, can observe galaxies so distant that their light has been traveling for more than 13 billion years. We're seeing these galaxies as they appeared just a few 100 million years after the Big Bang, when the universe was still in its infancy. These galaxies are now well beyond the cosmic event horizon. We can never reach them, but we can see them, we can study them, we can learn from them. And in doing so, we connect with parts of the universe that are fundamentally separated from us in space but not in time. The light that left those galaxies billions of years ago is reaching us now, creating a bridge across the void. This is the paradox at the heart of cosmology. The farther we look into space, the farther we look back in time. The most distant objects we observe exist in our past. By the time their light reaches us, they've changed, evolved, perhaps even died. We're seeing ghosts, echoes of things that once were. But those echoes tell stories. They reveal the processes that shaped the cosmos. They show us how galaxies formed, how stars were born, how the elements were created. They connect us to a history that stretches back to the beginning of time itself. So perhaps the question isn't how far can we travel? Perhaps the question is, how much can we know? How deeply can we understand the universe we inhabit? And viewed through this lens, the cosmic horizon isn't a wall, it's a window, a finite window to be sure, but a window nonetheless. Within that window lies more than we could ever fully explore, even with billions of years at our disposal. 2 trillion galaxies, each with hundreds of billions of stars, each of those stars potentially hosting planets. The sheer number of worlds, the diversity of environments, the possibilities for discovery. It's overwhelming, humbling, awe-inspiring. Let me give you some perspective on just how vast the reachable universe actually is, even with all the limits we've discussed. Our Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. That's a number so large it defies comprehension. If you tried to count them one per second, it would take you more than 10,000 years to count them all. And that's just our galaxy. Within the local group, which remains gravitationally bound and therefore permanently accessible to us, there are at least 80 galaxies. The largest of these is Andromeda, containing roughly 1 trillion stars. That's trillion with a T. Now let's think about what that means for planets. Based on data from the Kepler Space Telescope and other planet-hunting missions, we now know that planets are common. Most stars have them. Conservative estimates suggest there are at least as many planets as stars, possibly several times more. So within just our galaxy, we're looking at hundreds of billions of planets. Rocky worlds, gas giants, ice worlds, ocean worlds, desert worlds, planets orbiting close to their stars, scorched and airless. Planets in the habitable zone where liquid water could exist on the surface. Rogue planets drifting through interstellar space, untethered to any star. The diversity is staggering, and within that diversity, how many might harbor life? We don't know. That's one of the great unanswered questions in science. But even if life is incredibly rare, even if only 1 in a million planets develops biology, we're still talking about hundreds of thousands of living worlds in our galaxy alone. And that's just simple life, complex life, intelligence, civilization. Those might be even rarer. Maybe only 1 in a billion planets develops technological civilizations. Even so, that's still hundreds of civilizations in the Milky Way. Potential friends, potential teachers, potential mirrors in which we might see reflected our own hopes, fears, and dreams. The point I'm making is this. Even within the boundaries imposed by physics, even within the shrinking bubble of the reachable universe, there's more to explore than we could accomplish in millions of years. If humanity survives, if we spread beyond Earth, if we learn to travel between stars even at a fraction of light speed, the local group alone provides an essentially infinite frontier. You could spend 1 billion years exploring our galaxy and never see the same thing twice. Every star system is unique. Every planet tells a different story. But there's something else we need to talk about. Something that makes the distant future even stranger and more unsettling than you might imagine. We've discussed how the universe is expanding, how dark energy is accelerating that expansion, how galaxies are slipping beyond our reach. But what happens in the deep future? What does the universe look like trillions of years from now? This is where cosmology becomes almost philosophical, where science fiction and science fact blur together in the strangest ways. Current cosmological models, based on observations from missions like the Planck satellite and the Dark Energy Survey, suggest we live in what's called a lambda CDM universe. Lambda represents the cosmological constant, which is another name for dark energy. CDM stands for cold, dark matter. According to this model, the universe will continue expanding forever. The acceleration caused by dark energy will never stop. In fact, it will continue to increase. This leads to a scenario cosmologists call the Big Freeze, or sometimes the heat death of the universe. Here's what happens. Over the next few trillion years, star formation gradually slows down. Stars form when clouds of gas collapse under their own gravity, but as the universe expands, these gas clouds become more diffuse, more spread out. Eventually, all the available hydrogen and helium will be locked up inside stars or dispersed so thinly that new stars can't form. The last stars will ignite, burn through their fuel, and die. The universe will grow dark. The only objects left will be stellar remnants. White dwarfs, slowly cooling over trillions of years. Neutron stars spinning silently in the void. Black holes gradually evaporating through Hawking radiation over timescales that make the current age of the universe seem like the blink of an eye. As expansion continues, galaxies that are currently within the local group will remain bound together by gravity, but everything beyond that will recede beyond the cosmic horizon. In about 150 billion years, every galaxy outside our local group will have disappeared from view. An observer in the far future, looking up at the sky, would see only the galaxies of the local group. Everything else would be gone, not destroyed, but simply unreachable and unobservable. The universe would appear to be just a small island of matter surrounded by infinite darkness. And even that island won't last forever. Over timescales of 10 to the 100 years, that's a 1, followed by 100 zeros, even the atoms themselves might decay. Protons, which we currently believe are stable, might have a finite lifetime. If so, all ordinary matter will eventually dissolve into a thin soup of radiation and subatomic particles. The organized structures we see today, stars, planets, galaxies, even atoms, will be gone. All that will remain are black holes, and even those will eventually evaporate through Hawking radiation. The last black holes, the supermassive ones at the centers of galaxies, won't evaporate until about 10 to the 100 years from now. After that, pure emptiness, a universe of maximum entropy where nothing interesting can ever happen again. No change, no structure, no life. Just an infinite, eternal, empty void, slightly above absolute zero, with the occasional random quantum fluctuation being the only event in a featureless desert of space-time stretching out forever. This is the ultimate fate predicted by our current understanding of cosmology. It's called the heat death, and it's one of the most depressing conclusions science has ever reached. But here's something fascinating. This prediction assumes our current understanding is correct. It assumes dark energy remains constant, that the laws of physics don't change, that we understand the fundamental nature of reality. History suggests we should be humble about such assumptions. Every time we've thought we understood the universe completely, nature has surprised us. Newton's gravity worked perfectly until Mercury's orbit showed tiny discrepancies that required Einstein's general relativity. Classical physics worked beautifully until experiments at the atomic scale forced us to invent quantum mechanics. We thought the universe was static until Hubble discovered expansion. We thought expansion was slowing until observations of distant supernovae revealed acceleration. Who's to say we won't discover something new, some deeper principle we haven't yet imagined? Maybe dark energy isn't constant. Maybe it evolves over time. Some models suggest dark energy could increase, leading to a big rip where the fabric of space tears itself apart. Other models suggest it could decrease or even reverse, leading to a big crunch where expansion stops and everything collapses back into a singularity. There are even more exotic proposals. Cyclic universes that expand and contract eternally. Multiverse scenarios where our universe is just one bubble in an infinite foam. Simulated realities where the laws of physics are parameters that can be adjusted. I'm not saying any of these alternatives are correct. I'm saying we don't know. And the honest acknowledgement of uncertainty is one of science's greatest strengths. We follow the evidence wherever it leads, but we remain open to the possibility that our current models are incomplete. In fact, we know they're incomplete. General relativity and quantum mechanics, our two most successful physical theories, are fundamentally incompatible. At the extremes where both become important, like inside black holes or at the moment of the Big Bang, our equations break down. They give nonsensical answers, infinities that shouldn't be there. This tells us we're missing something, some deeper theory that unifies quantum mechanics and gravity into a coherent framework. String theory, loop, quantum gravity, causal dynamical triangulation. These are attempts to find that deeper theory. None have been experimentally confirmed yet. They remain mathematical frameworks searching for physical validation. But if and when we do discover a theory of quantum gravity, it might reveal entirely new possibilities. Maybe space-time itself emerges from something more fundamental. Maybe the Big Bang wasn't the beginning, but a transition from some prior state. Maybe the universe is far stranger than we currently imagine. This uncertainty, this admission that we don't have all the answers, is actually beautiful. It means the universe can still surprise us. It means there's always more to discover, more to learn, more to wonder about, and that brings me back to the question of limits. Yes, there are absolute limits based on our current understanding, the speed of light, the expansion of space, the cosmic event horizon. These are real boundaries derived from well-tested theories, but they're boundaries within our current framework. If the framework itself is incomplete, and we know it is, then perhaps there are loopholes we haven't discovered yet. I want to be very clear here. I'm not encouraging wishful thinking or dismissing established physics. The laws of relativity and the expansion of the universe are supported by mountains of evidence. When I say we should remain open to possibilities, I don't mean we should expect warp drives and wormholes to materialize just because they'd be convenient. I mean, we should maintain intellectual humility. We should remember that the universe is under no obligation to match our intuitions or desires. It simply is what it is, and our job as curious beings trying to understand it is to follow the evidence with rigor and honesty. That said, let's return to the practical reality we face right now in this universe, with the laws of physics as we currently understand them. Even if future discoveries reveal new possibilities, we can't count on them. We have to work with what we know. And what we know suggests that interstellar travel, while not impossible, is extraordinarily difficult. It will require innovations in propulsion, in life support, in engineering, at scales we've never attempted. It will require societies willing to invest resources into projects that span generations. It will require a long-term view that transcends quarterly earnings reports and election cycles. Some people find this depressing, the idea that most of the universe is forever beyond our reach, that we're confined to a tiny bubble of space-time, an island in an infinite ocean. But I see it differently. I see it as a gift, a constraint that focuses our attention on what matters. If we could reach any galaxy instantaneously, would we appreciate any of them? Would we take the time to truly understand the worlds within our reach? Constraints breed creativity. Limits force us to think carefully about priorities and values. Think about Earth for a moment. Our pale blue dot, as Carl Sagan called it. This single planet, orbiting an average star in an unremarkable region of an ordinary spiral galaxy, contains an almost infinite diversity of experiences. Towering mountains and deep ocean trenches, scorching deserts and frozen tundras, rainforests teeming with life and barren volcanic landscapes that look like alien worlds. We've been exploring Earth for our entire existence as a species, hundreds of thousands of years, and we're still finding new things. New species in the deep ocean, hidden caves beneath ice sheets, ancient ruins revealing forgotten civilizations. If one planet can sustain that much exploration and discovery, imagine what hundreds of billions of planets could offer. Even within the constraints of the cosmic horizon, even limited to the local group, we have access to more worlds than we could ever fully explore. Each one is unique. Each one has its own story written in rock and ice and atmosphere. Some might harbor life. Others might hold resources we can't even imagine. Still others might simply be beautiful, worth visiting for no other reason than to witness their strange landscapes and alien skies. And here's something that really gets me thinking. If humanity does survive long enough to become a truly spacefaring species spreading beyond Earth, establishing settlements throughout the solar system and eventually beyond, what would that mean for our identity? What does it mean to be human when humanity is scattered across multiple star systems, separated by light years of space with years or decades of communication delay between outposts? Would we remain one unified species, or would we diverge into different branches, adapted to different environments, developing different cultures, and eventually different biologies? This isn't idle speculation, it's evolutionary biology applied to cosmic timescales. If humans settle on Mars, They'll live in lower gravity, with different radiation exposure, different environmental pressures. Over thousands of generations, natural selection will push them in different directions than people living on Earth. Maybe they'll develop stronger bones to compensate for low gravity. Maybe their eyes will adapt to the dimmer sunlight. Maybe their social structures will evolve to fit the constraints of living in sealed habitats on a hostile world. Now multiply that by thousands of colony worlds, each with its own unique environment, each applying different selection pressures. After 1 million years, would the descendants of humans on different worlds even recognize each other as the same species? This raises profound questions about continuity and identity. Is humanity defined by our DNA, which would change over time? By our culture, which would diversify across the stars? By our values, which might evolve in unpredictable ways? Or is there some essential quality, some spark of consciousness, or creativity or curiosity, that makes us human regardless of physical form? These aren't just philosophical puzzles, they're practical questions that any successful interstellar civilization would have to grapple with. And then there's the question of time perception. We experience time on human scales, days, years, a human lifetime of perhaps 80 or 90 years if we're lucky, but the universe operates on vastly different time scales. Stars live for billions of years. Galaxies collide over hundreds of millions of years. The expansion of the universe unfolds over trillions of years. For a civilization attempting to explore the cosmos, this mismatch creates challenges. Do you send generation ships where the descendants of the original crew arrive at the destination centuries later? Do you use suspended animation or time dilation to compress the subjective journey time? Or do you simply accept that interstellar exploration is a multi-generational project, where those who begin the journey never see its completion? Each approach has implications. Generation ships require maintaining culture and purpose across multiple lifetimes. Imagine being born on a ship, spending your entire life aboard, raising children who will also live their entire lives aboard, all in service of a mission to reach a destination your great-great-great-grandchildren might see. What keeps that society cohesive? What prevents drift from the original mission? History shows us that societies change, that values shift, that purposes can be forgotten or reinterpreted. A journey lasting centuries provides ample time for all of that to happen. Suspended animation or cryogenic freezing, if we ever master it, sidesteps some of these issues but creates others. What if the technology fails? What if you wake up partway through the journey to find something has gone wrong? What if you arrive at your destination only to find that faster ships launched after you already arrived and established colonies? Technology progresses at an accelerating pace. The ships we launch tomorrow will be faster than the ones we launch today. This creates a strange scenario where it might make sense to wait, to delay your mission until better technology is available, except that future you might reason the same way, delaying again ad infinitum. At some point, you have to launch, or you never will. Time dilation is perhaps the most unsettling option. As we discussed earlier, traveling at relativistic speeds causes time for you to pass more slowly than time for the rest of the universe. You could travel to a star 50 light-years away, and from your perspective, the journey might take only a few years, but 50 years would pass on Earth. Your family, your friends, everyone you knew would age 5 decades while you aged only a few years. And if you ever returned, you'd find a world that had moved on without you. You'd be a stranger in your own homeland, a relic from the past, surrounded by people who have no memory of the world you left. This is the price of relativistic travel. You can cover vast distances in reasonable subjective time, but you can never truly go home. You become unstuck in time, drifting forward through the centuries while experiencing only years or decades. Some people might embrace this, the opportunity to see the future, to witness how civilization evolves. Others would find it unbearable. The loss of everything familiar, the severing of all connections. It's not just a journey through space, it's a journey through time with no return ticket. Now let's talk about something that doesn't get discussed enough: the psychological challenges of deep space exploration. We have some data from astronauts who've spent months or years on the International Space Station, and from researchers who've spent extended periods in isolated environments like Antarctic research stations. The findings are sobering: isolation, confinement, monotony. These take a toll. Even with the most carefully selected, highly trained individuals, problems emerge. Interpersonal conflicts, depression, anxiety, a phenomenon called the third quarter effect, where morale drops significantly around the 75% mark of a long mission as the initial excitement has worn off, but the end still seems distant. Now imagine not months in space, but years, decades, generations. How do you maintain mental health when you're sealed inside a metal can, hurtling through the void, surrounded by radiation and vacuum, with no possibility of rescue if something goes wrong? How do you deal with the knowledge that Earth is slipping further away with every passing day, becoming just another star in the sky, then fading from view entirely? Psychologists have proposed various countermeasures. Virtual reality to simulate natural environments, carefully designed social structures to minimize conflict, work rotations to prevent burnout. But these are educated guesses, not proven solutions. We simply don't know how the human psyche responds to truly long-duration spaceflight because we've never attempted it. And there's another factor we haven't discussed: cosmic radiation. Here on Earth, we're protected by a magnetic field and a thick atmosphere that shield us from the worst of space's radiation environment. But in interstellar space, there's no such protection. High-energy particles, cosmic rays accelerated to near-light speed by supernovae and other violent cosmic events, sleeting through space. When they strike living tissue, they damage DNA, increasing cancer risk, potentially causing cognitive problems. Long-term exposure is a serious concern for any interstellar mission. You can shield against radiation, but shielding is heavy. The more shielding you add, the more massive your spacecraft becomes, which means more energy required for propulsion, which means larger engines, more fuel, higher costs. Everything in spacecraft design is a trade-off. You can't optimize for everything simultaneously. You have to make choices. Do you prioritize speed or safety, comfort or efficiency, scientific instruments or life support redundancy? Every gram counts when you're trying to accelerate to relativistic velocities. These practical challenges don't get as much attention as the sexy physics of warp drives and wormholes, but they're just as fundamental to the question of interstellar travel. Even if we solve the propulsion problem, even if we find a way to achieve significant fractions of light speed, we still need to keep humans alive and sane for the duration of the journey. That's not a trivial problem. It might be harder than the propulsion itself, but let's assume we solve it. Let's imagine a future where we've developed robust life support systems, psychological protocols for long-duration missions, effective radiation shielding, and propulsion systems capable of reaching 10 or 20% of light speed. What then? Where do we go? How do we choose our destinations? This is where exoplanet research becomes crucial. Over the past 3 decades, since the first confirmed detection of an exoplanet in 1992, we've discovered thousands of worlds orbiting other stars. The Kepler mission alone found over 2,600 confirmed planets before it ended operations in 2018. These discoveries have revolutionized our understanding of planetary systems. We now know that planets are common, that solar systems come in wild varieties we never anticipated. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun, super-Earths, rocky worlds larger than Earth but smaller than Neptune, mini-Neptunes, ice giants dominating the mid-range of planetary masses, ocean worlds, lava worlds, desert worlds. The diversity is astonishing, and among this diversity we've found planets in the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface. Liquid water is considered crucial for life as we know it. Every living thing on Earth requires water. It's an excellent solvent, facilitating the chemical reactions that drive biology. So when we look for potentially habitable worlds, we look for planets in the habitable zone. But habitability is about more than just temperature. You need a stable atmosphere, a magnetic field to shield against radiation, geological activity to recycle nutrients, the right combination of elements, probably a large moon to stabilize the planet's axial tilt, preventing wild climate swings. Many factors have to align. The nearest potentially habitable exoplanet we know of is Proxima Centauri b, orbiting the closest star to our solar system, Proxima Centauri, which is part of the Alpha Centauri system. Discovered in 2016, Proxima b is roughly Earth-sized and orbits within the habitable zone of its star. At just 4.24 light-years away, it's about as close as we could hope for. But there's a catch, actually several catches. Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. Red dwarfs are notorious for violent flares, massive bursts of radiation, and charged particles that could strip away a planet's atmosphere over time. Proxima b orbits very close to its star, completing an orbit every 11 days. This close proximity means the planet is likely tidally locked, with one side permanently facing the star and the other side in eternal darkness. Could life exist there? Possibly. We don't know. The planet might have a thick enough atmosphere to redistribute heat from the day side to the night side. There might be a twilight zone along the terminator, the boundary between light and dark, where conditions are more temperate. Or the entire planet might be a frozen wasteland on one side and a scorched desert on the other, with any water long since evaporated or frozen. We won't know until we send a probe to look. And that brings us back to the breakthrough starshot concept. Those tiny light sail probes, accelerated to 20% of light speed, could reach Proxima Centauri in about 20 years. They'd fly through the system at incredible velocity, gathering data for just a few minutes, then transmitting that data back to Earth. Think about what that means. We could know within our lifetimes whether there's anything interesting at our nearest stellar neighbor. We could see actual images of an exoplanet from close range, not fuzzy dots or indirect measurements, but real photographs of alien landscapes. We could measure the composition of its atmosphere, search for biosignatures, gases that might indicate the presence of life, oxygen, methane, phosphine. These molecules don't last long in an atmosphere unless something is constantly producing them. On Earth, that something is biology. Finding them elsewhere would be a strong hint that we're not alone. But let's be realistic about timescales. Breakthrough Starshot remains a concept, not an actual mission. The technology required doesn't exist yet. Building a 100-gigawatt laser array would be a mega project requiring decades and enormous investment. Developing gram-scale spacecraft with cameras, computers, and transmitters powerful enough to send data across 4 light-years is an incredible engineering challenge. Even if everything goes perfectly, we're probably looking at mid-century at the earliest before such a mission could launch. Add 20 years of travel time and 4 years for the signal to return, and we're looking at results sometime in the 2070s or 80s. That's assuming the project even happens, which is far from certain. More likely, our first detailed look at an exoplanet will come from next-generation space telescopes. The James Webb Space Telescope, launched in 2021, has already begun characterizing exoplanet atmospheres using a technique called transit spectroscopy. When a planet passes in front of its star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere. Different molecules absorb different wavelengths, leaving distinctive fingerprints in the spectrum. By analyzing these fingerprints, we can determine what gases are present. Webb has already detected water vapor, carbon dioxide, and other molecules in the atmospheres of several exoplanets. Future telescopes will push this capability further. Concepts like the Habitable Exoplanet Observatory, or HabEx, and the Large UV Optical Infrared Surveyor, or LUVOIR, could directly image Earth-sized planets in the habitable zones of nearby stars. Not just detect them indirectly, but actually see them as distinct points of light separated from their stars. This would allow detailed spectroscopic analysis, searching for biosignatures and technosignatures, indicators of technological civilizations. These missions are still in the planning stages, with potential launches in the 2040s or beyond, but they represent our best near-term hope for answering the question, are we alone? And that question matters profoundly to our discussion about the limits of space travel. If life is common, if biology arises wherever conditions permit, then the universe is filled with living worlds, perhaps trillions of them. In that case, the cosmic horizon doesn't limit our access to life. There's plenty within reach, but if life is rare, if Earth is a genuine anomaly, then the accessible universe might contain very few biospheres. And if intelligent life is rarer still, we might be functionally alone within our cosmic horizon. The nearest civilization could be billions of light years away, forever beyond our ability to contact or visit. This scenario, often called the Great Silence or the Fermi Paradox, asks why, if civilizations are common, we haven't detected any. Where is everybody? The answer might be that space is simply too vast, the distance is too great, the timescales too long. Civilizations might arise, flourish for a few million years, then vanish, all without ever overlapping with another civilization in time and space. Or maybe intelligence is vanishingly rare, a cosmic accident that has occurred only once here on Earth. We don't know. And until we either find evidence of other life or conduct exhaustive surveys that find nothing, we won't know. But let's think about what happens if we do find evidence of another civilization. Imagine we detect a radio signal, clearly artificial, coming from a star 50 light-years away. That signal left their planet 50 years ago. By the time we receive it, decode it, compose a response and send it back, 100 years will have passed since they originally transmitted. Conversations at this pace are barely conversations at all. You could send a message and never live to hear the reply. Multiple generations might pass between exchanges. This is what interstellar communication looks like when you're constrained by the speed of light. Yet even with this limitation, the exchange of information could be profoundly valuable. Mathematics, physics, chemistry. These are universal. Any technological civilization must understand them. We could share scientific knowledge, cultural information, philosophical perspectives. We could learn that intelligence has arisen elsewhere, that we're part of a larger community of minds scattered across the galaxy, connected not by proximity, but by shared curiosity. That knowledge alone, the certainty that we're not alone, would transform humanity's self-understanding. We'd no longer be the universe's only experiment in consciousness. We'd be one among many. And here's something fascinating. Information can travel at light speed, but it can carry blueprints for technologies, designs for tools, instructions for building things we haven't imagined. If another civilization has solved problems we're still wrestling with, they could transmit the solutions. Of course, there's no guarantee those solutions would work with our technology or materials, but the principles might be transferable. This is how information extends our reach beyond the physical. We can't visit a civilization 50 light-years away, but we can exchange knowledge with them. In a sense, ideas are the only things that truly travel at light speed. Now let's return to a question I raised earlier. What does it mean to be somewhere? In the age of telecommunications, virtual reality, and remote sensing, physical presence is only one form of existence. When you video call someone on the other side of Earth, you're interacting with them in real time despite being thousands of kilometers apart. The interaction feels immediate, intimate, present. Now extend that concept. If we deploy swarms of robotic probes throughout the galaxy, each equipped with sensors, cameras, and AI capable of exploring and analyzing their environments, are we not in some sense present in those places? The probes are extensions of our senses and our will, avatars representing humanity in distant star systems. Some futurists have proposed exactly this approach to cosmic exploration. Instead of sending humans, we send machines. Small, durable, intelligent machines that can survive the radiation, the isolation, the vast timescales involved. They could be self-replicating, using local materials to build copies of themselves, spreading exponentially throughout the galaxy. This concept, known as von Neumann probes after mathematician John von Neumann, who studied self-replicating systems, could theoretically explore the entire galaxy within a few million years, even traveling at modest sublight speeds. Why haven't we detected such probes from other civilizations? That's another facet of the Fermi paradox. If self-replicating probes are a good idea, and if other civilizations exist and thought of it, where are they? Perhaps the galaxy is already full of such probes, but they're small and quiet, observing without interfering, and we haven't noticed them. Or perhaps self-replicating machines are inherently dangerous, prone to evolving in unpredictable ways, and wise civilizations avoid building them. Or perhaps we're truly the first, the earliest civilization to arise in our corner of the cosmos, and the galaxy is genuinely empty, waiting for us to fill it. That possibility that we might be first carries enormous responsibility. If we're the seed from which intelligence spreads throughout the galaxy, then our choices matter cosmically. The values we encode into our exploring machines, the ethics we follow as we venture outward, these will shape the future character of galactic civilization. Do we exploit every resource we find, or do we preserve and protect? Do we seek to dominate, or do we seek to understand? These aren't just practical questions, they're moral questions, with implications that stretch across light years and eons. And let me share something that gives me hope. Despite all our flaws, despite our history of conflict and destruction, humanity has also shown remarkable capacity for cooperation, curiosity, and compassion. We've built the International Space Station, a laboratory in orbit assembled by 15 nations working together. We've sent robots to Mars that were designed and operated by international teams. We've created the Internet, a global network connecting billions of people, enabling collaboration and communication across all boundaries. When we face challenges that affect everyone, when the stakes are high enough, we can work together. Space exploration, by its nature, tends to bring out our better angels. There's something about looking up at the stars that makes our earthly divisions seem petty. The astronauts who've seen Earth from orbit often describe a profound shift in perspective, sometimes called the overview effect. Seeing our planet as a fragile blue marble suspended in the void, with no visible borders, no signs of conflict, just a beautiful, unified whole. This perspective doesn't solve all our problems, but it reminds us what we have in common. We're all passengers on the same spacecraft, Earth, traveling through the cosmos together. And that brings me to a critical point about the limits of space travel. The biggest obstacles aren't just physical, they're also social, political, and economic. We have the scientific knowledge to begin serious interstellar missions, not with humans yet, but with robotic probes. The technology exists, or could exist, with focused development. What we lack is the collective will and the sustained commitment. Building an interstellar probe mission would cost tens of billions of dollars, require decades of development, and deliver results long after the politicians who approved the funding have left office. Our current political and economic systems are optimized for short-term thinking, quarterly profits, election cycles, immediate results. But space exploration operates on different timescales. The Voyager missions, launched in 1977, are still returning data 49 years later. The Hubble Space Telescope, launched in 1990, has been operating for 36 years, revolutionizing astronomy generation after generation. The James Webb Space Telescope required more than 20 years of development before its launch in 2021. These are multi-decade projects requiring sustained funding and commitment across changes in administration, shifts in priorities, and economic ups and downs. The fact that we've managed to complete any of them is actually remarkable. Now imagine trying to maintain that commitment not for decades, but for centuries. That's what serious interstellar exploration would require. Even with optimistic propulsion systems, missions to nearby stars would take decades to arrive, and years more to transmit data back. The people who plan the mission won't live to see its success. Maybe their children won't either. You have to believe in something larger than yourself. Invest in a future you'll never personally experience. That's a hard sell in a world focused on immediate gratification and tangible returns. Yet we've done it before in other contexts. The great cathedrals of medieval Europe took centuries to complete. Generations of workers, artisans, and architects devoted their lives to projects they knew they'd never see finished. They did it for faith, for legacy, for the belief that some things are worth doing even if you don't personally benefit. Planting a tree you'll never sit under, building a future for people you'll never meet. This capacity for long-term thinking, for delayed gratification in service of larger goals, is part of what makes us human. We're capable of it. The question is whether we'll choose it. There's also the question of priorities. With limited resources, how do we decide what to invest in? Exploring distant star systems or solving problems here on Earth, feeding the hungry, housing the homeless, curing diseases, addressing climate change. These are urgent, immediate needs affecting billions of people right now. How do you justify spending billions on space exploration when there's so much suffering on Earth? It's a legitimate question, and it deserves a serious answer. Here's my take. It's not either or, it's both and. The resources spent on space exploration are a tiny fraction of global spending. NASA's budget, for example, is less than 0.5% of the United States federal budget. The entire global space industry, including all commercial and government activities, represents a small sliver of the world economy. We can address earthly problems and explore space. In fact, many technologies developed for space have terrestrial applications. Satellite imaging helps track climate change, manage agriculture, respond to disasters. Water purification systems developed for the International Space Station provide clean water in regions lacking infrastructure. Medical devices, materials science, computational techniques. The spin-offs are real and valuable, but beyond practical benefits, there's something deeper. Exploration is part of what it means to be human. We're curious creatures, we ask questions, we seek to understand. This drive has led us to the tops of mountains, the depths of oceans, the poles of our planet. Now it's leading us into space. Suppressing that curiosity, that urge to explore, would diminish us. We'd be less than we could be. And there's evidence that inspiring goals, grand projects that capture the imagination, actually motivate people to tackle other challenges. The Apollo program inspired a generation to enter science and engineering. Many of those people went on to make contributions far beyond space exploration, so I reject the premise that we must choose between Earth and space. We need both. We need to take care of our home planet. Absolutely. But we also need to look outward, to dream big, to attempt things that seem impossible. That's how we grow, that's how we evolve. And in practical terms, becoming a spacefaring civilization improves our chances of long-term survival. Earth faces risks, asteroid impacts, supervolcano eruptions. Eventually, billions of years from now, the sun will expand and consume our planet. If humanity remains confined to one world, we're vulnerable. Spreading to multiple worlds, multiple star systems, provides resilience. It's the ultimate backup plan. But let's be honest about timescales. Even the most optimistic projections for interstellar colonization involve thousands or millions of years. We're talking about the very long-term future of humanity, assuming we survive the next few centuries, which is far from guaranteed. Climate change, nuclear weapons, artificial intelligence, biotechnology. We've developed the power to alter our world and potentially destroy ourselves. The next century will determine whether we navigate these dangers successfully or succumb to them. Space exploration is a long-term dream, but first, we have to survive the short term, and that's where the cosmic perspective becomes valuable. When you understand the scale of the universe, the billions of galaxies, the trillions of stars, the incomprehensible vastness of space and time, it changes your priorities. The things we fight over, borders and resources and ideologies, they start to seem less important, not unimportant, but less all-consuming. We're all human. We're all inhabitants of the same tiny planet in an enormous cosmos. We have more in common with each other than we do with anything else in the universe. That realization, that cosmic perspective, might be exactly what we need to solve our earthly problems. Carl Sagan captured this beautifully in his book, Pale Blue Dot, reflecting on an image of Earth taken by Voyager 1 from beyond Neptune. He wrote about how everyone who's ever lived on that pale blue dot, suspended in a sunbeam. Every hero and coward, every creator and destroyer, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. That perspective is humbling. It reminds us that our planet is precious, irreplaceable, the only home we've ever known. It also reminds us that the universe is vast beyond comprehension, and we're a tiny part of it. Both truths matter. We're small, but we're not insignificant. We're matter that has become aware of itself, atoms organized in such a way that they can contemplate their own existence and ask questions about the cosmos. That's extraordinary. That's worth celebrating and preserving. Now let's talk about something that doesn't get enough attention: the ethical dimensions of space exploration and colonization. If we do spread beyond Earth, if we establish settlements on Mars, on moons of Jupiter and Saturn, eventually around other stars, what responsibilities do we have? To each other, certainly, but also to the environments we enter. If we find life elsewhere, even simple microbial life, do we have the right to disturb it, to potentially contaminate it with Earth organisms, to exploit the resources of that world? These questions are addressed in a field called planetary protection, which develops protocols to prevent contamination between worlds. Current guidelines require sterilization of spacecraft going to places where life might exist, like Mars or Europa. We don't want to accidentally introduce Earth microbes that could outcompete native life. But these protocols assume we're exploring uninhabited or microscopically inhabited worlds. What if we find something more? What if there are ecosystems, complex life, perhaps even intelligence? The good news is that most of the universe appears to be lifeless, rocky planets and moons devoid of biology, where we could establish settlements without ethical concerns about displacing native life. The bad news is we won't know for sure until we look closely, and by the time we discover life, we might already be committed to a colonization effort. These are questions we need to think about now before we're faced with them in practice. What are our values as we venture into the cosmos? What kind of civilization do we want to be? I believe we should approach space exploration with humility and care, not as conquerors, but as students, not seeking to dominate, but to understand. The universe has much to teach us if we're willing to listen, and if we find life in any form, we should treat it with respect. Not as a resource to be exploited, but as a fellow outcome of cosmic evolution worth studying and protecting. This ethical approach doesn't just apply to alien life. It applies to how we treat each other as we expand into space. Will future space settlements be inclusive, or will they replicate the inequalities and injustices of Earth? Will they be democratic or authoritarian? Will they value diversity or enforce conformity? These aren't abstract questions. The societies we establish beyond Earth will shape the long-term future of humanity. If we get it wrong, if we export our worst tendencies into space, we'll simply spread suffering across a larger volume. But if we get it right, if we learn from our mistakes and build something better, space offers a genuine opportunity for a fresh start, not to escape Earth's problems, but to apply the lessons we've learned, to create societies based on cooperation, sustainability, and respect for life in all its forms. Let's return now to the hard physics and think about what all of this means for the absolute limits of human travel. We've established that the cosmic event horizon, currently about 16.5 billion light-years away, represents a fundamental boundary. Galaxies beyond that distance are receding faster than light can travel through the expanding space between us. Even if we left today, traveling at light speed, we could never reach them. The finish line keeps moving away faster than we can approach it. This isn't a technological limitation, it's a feature of space-time itself. But within that boundary, within the sphere of the reachable universe, there's still an enormous amount of territory. Based on calculations by physicists studying cosmic expansion and dark energy, approximately 5% of all galaxies in the observable universe remain theoretically accessible. That's roughly 100 billion galaxies, each containing hundreds of billions of stars. The numbers are so large they lose meaning, but let's try to put it in perspective. If humanity became a truly spacefaring civilization, spreading at a significant fraction of light speed, we could potentially reach thousands, millions, perhaps even billions of star systems over the coming millions of years. But here's the cruel mathematics of expansion. The reachable universe is shrinking, not in absolute size, but in the number of galaxies it contains. Every moment, galaxies slip across the event horizon, transitioning from reachable to unreachable. The Dark Energy Survey and observations from the DESI project, which released major results in 2024, have refined our measurements of how fast this is happening. The current acceleration rate suggests that within about 150 billion years, every galaxy outside our local group will have crossed the event horizon. They'll disappear from view, their light redshifted into invisibility, forever beyond our reach. 150 billion years sounds like a long time, and it is by any human measure. It's roughly 11 times the current age of the universe, but on cosmic timescales, it's finite. It's a deadline. If any part of humanity survives into that distant future, they'll look up at the sky and see only the galaxies of the local group. Everything else will be gone. The universe will appear to be shrinking down to just our gravitationally bound island of matter, surrounded by infinite emptiness. Future astronomers might not even know that other galaxies once existed unless they have access to ancient records from our time. This creates a strange kind of cosmic urgency. Not an immediate crisis, but a long-term constraint. If humanity wants to explore beyond the local group, we need to do it while those distant galaxies are still accessible. Every billion years we wait, fewer destinations remain available. Now, I want to be clear, we're nowhere near the point where this should influence policy decisions. We have far more immediate concerns. But philosophically, cosmologically, it's sobering to realize that the universe isn't a static stage. It's dynamic, evolving, and the opportunities it offers are time-limited. There's another aspect of cosmic expansion that's worth contemplating. As space expands, the density of matter and energy decreases. The universe becomes more diffuse, more empty. Stars form from collapsing gas clouds, but as expansion continues, those clouds become less dense, making star formation more difficult. Eventually, all the available gas will either be locked up inside stars or spread so thin it can't collapse. The last stars will form, burn through their fuel, and die. After that, no new stars. The universe will grow dark. Current estimates suggest peak star formation occurred about 10 billion years ago. We're already past the peak. The universe is middle-aged, on the downslope toward an elderly future where new stars become increasingly rare. In about 1 trillion years, roughly 100 times the current age of the universe, star formation will effectively cease. Any civilizations existing at that time will live in a dying cosmos, watching the last stars flicker and fade. They'll be able to look back at our epoch, read about a younger universe filled with brilliant galaxies and abundant star formation, and know they'll never experience it themselves. This temporal asymmetry is fascinating and melancholy. The universe had a beginning, went through a vibrant youth, is now in middle age and faces a long, slow decline into darkness. We happen to exist during a relatively hospitable era. Stars still form, planets still coalesce, complex chemistry can occur. Billions of years from now, none of that will be true. The cosmic environment will be hostile in ways we can barely imagine. Cold, dark, entropy everywhere. Any intelligence surviving into that far future will face challenges we don't have to deal with. They might look back at our time with envy, wishing they could have experienced the universe when it was still young and full of light. But let's bring this back to human scales. Forget trillions of years. What about the next few centuries? What are the realistic prospects for human space travel in our lifetimes or those of our immediate descendants? The answer depends on what we choose to prioritize and invest in. Right now, in 2026, we're seeing a resurgence of interest in space exploration. Multiple countries have active space programs. China landed a rover on the far side of the moon. India successfully reached Mars and the moon. The United States is planning to return humans to the lunar surface through the Artemis program. Private companies like SpaceX are developing reusable rockets and planning missions to Mars. These are encouraging developments. They suggest that space exploration is becoming more accessible, not less. Reusable rockets, pioneered by SpaceX and now being adopted by other companies and agencies, dramatically reduce the cost of reaching orbit. When you can land a rocket and fly it again, rather than discarding it after one use. Economic shift. Launch costs drop. More missions become feasible. This trend is likely to continue. Better technology, economies of scale, increased competition. All of these factors point toward a future where space access becomes routine rather than exceptional. Within the next few decades, we might see permanent human settlements on the moon. These wouldn't be brief visits like the Apollo missions, but sustained presence. People living and working on the lunar surface for months or years at a time. Mining resources, conducting research, building infrastructure. The moon could become a proving ground for the technologies and techniques we'll need for more distant destinations. Low-gravity operations, radiation protection, closed-loop life support. All of these capabilities can be developed and tested on the moon, which is only 3 days away from Earth, before attempting the much longer journey to Mars. Mars is the next major goal for human space exploration. Multiple missions are being planned by various agencies and companies, with target dates ranging from the 2030s to the 2040s. Getting humans to Mars is significantly harder than getting them to the moon. The journey takes 6 to 9 months each way, depending on planetary alignment. Launch windows only occur every 26 months when Earth and Mars are properly positioned. Once you arrive, you can't immediately return. You have to wait for the next launch window, meaning a Mars mission involves at least 2 years away from Earth, possibly longer. The challenges are formidable, life support for such duration. Radiation exposure during the journey and on the Martian surface, which has no magnetic field and only a thin atmosphere. The psychological effects of isolation and confinement. The risk of equipment failure far from any possibility of rescue. Landing on Mars is difficult. The atmosphere is thick enough to require heat shields but too thin for parachutes alone. You need retro rockets, precision guidance, proven systems. And once on the surface, you need habitats, power systems, water extraction, food production, everything required to keep humans alive in a hostile environment. Despite these challenges, I believe we'll see humans on Mars within the next few decades, not because it's easy, but because it's achievable with focused effort and adequate resources. The technology exists or is close to existing. What's needed is commitment, and there are reasons to be optimistic. Multiple players are working toward this goal independently, increasing the chances that at least one will succeed. National prestige, scientific discovery, the pioneering spirit. These motivations drive space exploration, and they're not going away. But Mars is still in our solar system, still relatively close by cosmic standards. The real question is, can we go farther? Can we reach the stars? And if so, how long will it take? Earlier, we discussed concepts like laser sails and fusion rockets that could theoretically achieve 10 to 20% of light speed. These would make interstellar travel possible within human-relevant timescales, at least for nearby stars. But moving from concept to reality requires solving enormous engineering challenges and investing resources at scales we've never attempted. One interesting proposal that's been gaining attention is the concept of a seed ship. Instead of sending humans directly to another star system, you send the means to create humans, frozen embryos, or even just digital information encoding human DNA, along with artificial wombs and robotic systems capable of raising children. The ship travels for decades or centuries, arrives at the destination, and only then are humans brought into existence. These humans would be born in another star system, never having known Earth except through records and stories. This approach sidesteps many of the challenges of keeping living humans alive during an interstellar journey. No need for life support systems operating for centuries, no psychological issues from prolonged isolation, at least not during the journey, but it raises profound ethical questions. Is it right to create people who will be born light years from Earth with no possibility of return? Who will raise these children? Robots? AI? How do you ensure they receive the nurturing and education needed to develop into healthy, functional adults? How do you transmit culture, values, humanity itself across the void? These aren't just philosophical puzzles, they're practical problems any serious seed ship mission would have to address, and the answers aren't obvious. Maybe advanced AI could serve as caretakers and teachers. Maybe the ship includes extensive libraries of human culture, art, science, history. Maybe the first generation is raised to understand their unique role as the founders of a new branch of humanity. But would that be fair to them? To be born into such circumstances without choice? I don't have easy answers to these questions. I suspect no one does. They're the kind of dilemmas we'll have to grapple with if we're serious about interstellar colonization. And they highlight something important. The limits of space travel aren't just about physics and engineering. They're also about ethics, psychology, and what we value as a species. Even if we can do something, should we? And if we choose to do it, how do we do it responsibly with care for the well-being of everyone involved? Let me shift gears and talk about something that gives me genuine excitement. The prospect of robotic exploration in the near term. We don't need to solve the immense challenges of human interstellar travel to make profound discoveries. Robotic probes can go places humans can't, survive conditions that would kill us, operate for decades or centuries without resupply. And they're getting more sophisticated every year. The Mars rovers, Curiosity and Perseverance, carry incredibly advanced instruments. They can analyze rock chemistry, search for organic molecules, even collect samples for eventual return to Earth. The Europa Clipper mission, launched in October 2024, is on its way to Jupiter's moon, Europa. It'll arrive in 2030 and conduct detailed studies of the moon's icy surface and subsurface ocean. Europa is one of the most promising places in our solar system to search for life. Beneath its frozen crust lies an ocean of liquid water, possibly containing twice as much water as all of Earth's oceans combined. Where there's liquid water, organic molecules, and energy sources, there might be life. Europa Clipper won't land, but it'll analyze the composition of ice and any water vapor plumes erupting from the surface. If it detects organic compounds or other biosignatures, that would justify a follow-up mission with a lander or even a submarine probe. The Dragonfly mission, scheduled to launch in 2027 and arrive in 2034, will explore Titan, Saturn's largest moon. Titan is extraordinary. It has a thick atmosphere, liquid lakes and rivers on its surface, and complex organic chemistry. The catch is the liquid isn't water, it's methane and ethane. The surface temperature is minus 179 degrees Celsius, far too cold for liquid water. But Titan shows us that interesting chemistry, possibly even exotic forms of life, might exist in environments completely different from Earth. Dragonfly is a rotorcraft, a drone that will fly from location to location, sampling the atmosphere and surface, searching for chemical signatures of biological processes. These missions represent the cutting edge of solar system exploration. Within the next few decades, we'll have visited every major world in our solar neighborhood, from the scorching surface of Mercury to the icy plains of Pluto and beyond. We'll have searched for life in the subsurface oceans of Europa and Enceladus, the methane lakes of Titan, the ancient river valleys of Mars. We'll have analyzed the composition of dozens of moons, asteroids, and comets. This is the golden age of planetary science, and we're living through it. And it doesn't stop at the edge of our solar system. The next generation of telescopes will peer deeper into space than ever before. The James Webb Space Telescope is already revolutionizing our understanding of the early universe, detecting galaxies that formed just a few 100 million years after the Big Bang. Future missions will build on this foundation. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will conduct wide-field surveys, mapping large portions of the sky in infrared light. It'll search for exoplanets, study dark energy, and observe the structure of the universe on the largest scales. Ground-based telescopes are also advancing rapidly. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter. That's enormous, dwarfing current telescopes. It'll be able to directly image exoplanets, study the atmospheres of potentially habitable worlds, and observe the most distant galaxies with unprecedented detail. The Square Kilometre Array, a radio telescope being built in Australia and South Africa, will have a collecting area of 1 square kilometre distributed across thousands of individual antennas. It'll be 50 times more sensitive than any existing radio telescope, capable of detecting faint signals from the early universe and possibly even techno-signatures from alien civilizations. These instruments extend our reach across the cosmos in ways that complement physical travel. We can't visit distant galaxies, but we can observe them. We can't land on exoplanets orbiting other stars, but we can analyze their atmospheres and search for signs of life. This is exploration through information rather than presence. And while it's not the same as being there, it's profoundly valuable. Every photon that reaches our telescopes carries a message from across space and time. By learning to read those messages, we participate in the grand story of the cosmos. Now let's address something I've alluded to several times but haven't fully explored. The possibility that our understanding of physics is incomplete and that future discoveries might reveal new possibilities. This is speculative, but it's grounded in history. Physics has been revolutionized multiple times. Newtonian mechanics gave way to relativity and quantum mechanics. Our understanding of the universe expanded from a static cosmos to an evolving one with a beginning. We discovered dark matter and dark energy, components that make up 95% of the universe's mass energy, but which we still don't fully understand. Dark energy is particularly mysterious. We know it's causing the accelerated expansion of the universe. We can measure its effects, but we don't know what it is. The simplest explanation is that it's a property of space itself, a cosmological constant, but this raises deep questions. Why does it have the value it does? Could it change over time? Some theoretical models suggest dark energy might not be constant. It could evolve, potentially even reversing, from causing acceleration to causing deceleration. If that happened, the universe could transition from expansion to contraction, potentially ending in a big crunch. Other models propose that dark energy is actually a field, similar to the Higgs field that gives particles mass, but with different properties. This hypothetical field has been called quintessence. If quintessence exists and we could learn to manipulate it, that might open possibilities we haven't imagined. Could we locally alter the expansion of space, create bubbles of compressed or expanded space-time? These are wild speculations far beyond our current capabilities or understanding, but they illustrate that the universe might still have surprises in store. Similarly, quantum mechanics, for all its success, remains incomplete. It doesn't integrate with general relativity. At the Planck scale, where quantum effects and gravity both become important, our equations break down. We need a theory of quantum gravity, and we don't have one yet. String theory, loop quantum gravity, and other approaches attempt to provide that theory, but none have been experimentally confirmed. If and when we do develop a working theory of quantum gravity, it might reveal new aspects of space-time, new possibilities for travel or communication. Some speculative ideas emerging from these frameworks include the possibility that space-time has additional dimensions beyond the 3 spatial and 1 temporal dimension we experience. String theory, for instance, requires 10 or 11 dimensions for mathematical consistency. The extra dimensions are thought to be compactified, curled up so small we don't notice them. But what if there are ways to access or manipulate these extra dimensions? Could they provide shortcuts through space-time, enabling faster-than-light travel without violating relativity in our familiar 4 dimensions? Again, this is highly speculative. There's no evidence for extra dimensions, and even if they exist, accessing them might be impossible. But the point is, our current understanding of physics is provisional. It works extraordinarily well within its domain of applicability, but we know there are gaps. We know there are questions we can't yet answer. And history suggests that filling those gaps often reveals unexpected possibilities. I'm not saying we should expect magic wormholes or warp drives to materialize. I'm saying we should maintain intellectual humility and stay open to the possibility that nature is more subtle and surprising than our current theories suggest. That said, we have to work with the knowledge we have, not the knowledge we hope to gain. And based on current physics, the limits of space travel are real and constraining. Light speed is a hard limit. Cosmic expansion creates an event horizon. These aren't engineering challenges to be overcome with better technology. They're fundamental features of the universe we inhabit. Any future theory would have to explain why these features appear the way they do, and that explanation might involve even deeper reasons why certain things are impossible. So where does this leave us? We've explored the absolute limits of human travel through space from multiple angles. Physical limits imposed by relativity and cosmic expansion, engineering challenges of propulsion, life support, and radiation protection, social and economic barriers of cost and commitment, ethical considerations about how we explore and what responsibilities we have, and we've acknowledged the possibility, however remote, that future discoveries might change the picture. The bottom line is this: the reachable universe is vast but finite. It contains roughly 100 billion galaxies, each with hundreds of billions of stars, each potentially hosting planets. That's more than enough to keep us exploring for millions or billions of years. But 95% of the observable universe is forever beyond our reach, separated from us not by mere distance, but by the fundamental expansion of space-time. As time passes, the reachable portion shrinks. More galaxies cross the cosmic event horizon, transitioning from accessible to inaccessible. Within about 150 billion years, only our local group will remain. These limits are sobering but not depressing. They give context and meaning to our existence. We live in a specific place and time within cosmic history, a place and time where the universe is still young enough to be interesting, where stars still form, where galaxies still shine brightly, where exploration is possible. Billions of years from now, none of that will be true. We're fortunate to exist when we do, and within the boundaries we face, there's still room for extraordinary achievement. If humanity survives the challenges of the coming centuries, if we learn to live sustainably on Earth while reaching outward into space, we could become a truly interstellar species, not in the sense of conquering the galaxy overnight, but gradually, patiently, establishing footholds on nearby worlds. The Moon, Mars, the moons of Jupiter and Saturn, eventually the closest stars, Proxima Centauri, Alpha Centauri, Barnard's star. Each destination opens up new possibilities, new resources, new environments to study and potentially inhabit. This expansion would unfold over millennia, not decades. Each step would build on the previous one. Technologies developed for lunar settlements inform Mars missions. Lessons learned on Mars apply to the moons of the outer solar system. Experience in our solar system prepares us for interstellar journeys. It's a pyramid of progress where each level must be solidly established before the next can be built. There are no shortcuts, no cheat codes, just patient, persistent effort across generations. And that's actually beautiful in its own way. It means space exploration is a project for all of humanity, not just one generation or one nation. It means the work we do today, the missions we launch, the technologies we develop, they're not just for us. They're investments in a future we'll never see, but which wouldn't exist without our efforts. We're planting trees under whose shade we'll never sit. We're building cathedrals we'll never see completed. And there's something profoundly meaningful about that. Let me share a thought that's been with me throughout this entire exploration. The universe is under no obligation to be accessible to us. It could have been constructed in such a way that intelligent life was impossible, or that intelligence arose but could never develop technology, or that technology could develop but space travel was completely impossible. The fact that we exist, that we can think and wonder and explore, that we've figured out how to leave our planet and visit other worlds, that nearby stars are theoretically reachable even if distant galaxies are not. All of this is remarkable. We should be grateful for what's possible rather than bitter about what isn't. Consider what we've already accomplished. We've gone from being bound to Earth's surface to walking on another world, from wondering if other planets existed to discovering thousands of them, from speculating about the origin of the universe to measuring its age to within a fraction of a percent. We've sent probes to every planet in our solar system and beyond. We've built telescopes that can see galaxies billions of light years away. We've detected gravitational waves from colliding black holes. We've captured an image of a black hole's event horizon. Every single one of these achievements was impossible until we made it possible. And we're just getting started. We're only a few decades into the space age. The first artificial satellite, Sputnik, launched in 1957, just 69 years ago. The first human in space, Yuri Gagarin, flew in 1961. The first moon landing happened in 1969. On cosmic timescales, on even historical human timescales, this is the blink of an eye. We're infants in space, taking our first tentative steps. Imagine what we might accomplish given centuries, millennia, millions of years if we survive that long. The physicist Freeman Dyson once said something that resonates with me. He said that one of the great benefits of space travel is that it creates a new dimension along which the human species can escape from its problems. Not escape in the sense of running away, but escape in the sense of expanding beyond previous limits. When a species is confined to a single world, any catastrophe on that world threatens the entire species. But if that species spreads to multiple worlds, multiple star systems, it becomes much more resilient. No single catastrophe can threaten everything. This is the long-term justification for space exploration, not for next year or next decade, but for the next million years. Making humanity a multiplanetary, eventually multistellar species increases our chances of long-term survival. It distributes our eggs across many baskets. And in doing so, it ensures that consciousness, this remarkable property that allows matter to reflect on itself, doesn't disappear from the universe when our sun eventually dies. We carry the light of awareness with us to other worlds, keeping it burning long after Earth has been consumed by the expanding sun in about 5 billion years. But let's bring this back to the present moment. Back to you and me here and now, in 2026. What does all of this mean for us personally? Most of us will never travel to space. We'll live our entire lives on Earth within a few hundred kilometers of where we were born. Does the cosmic perspective still matter? I believe it does, profoundly. Understanding the scale of the universe, our place within it, the limits we face, and the possibilities that still exist changes how we see ourselves and our world. It provides context. When you understand that Earth is one planet among billions in our galaxy alone, that our galaxy is one among trillions in the universe, that we're made of atoms forged in ancient stars, it shifts your perspective. The problems that seemed overwhelming start to seem manageable. The divisions that seemed insurmountable start to seem arbitrary. We're all stardust. We're all temporary arrangements of matter that have somehow become conscious and capable of understanding the cosmos that created us. And there's responsibility in that understanding. We're the universe's way of knowing itself, at least in this tiny corner of space-time. As far as we know, we might be the only conscious minds within billions of light years. That makes us precious. Not in a self-aggrandizing way, but in a humbling way. We're rare, possibly unique, and that rarity imposes an obligation to preserve consciousness, to expand it, to use it well, to create rather than destroy, to understand rather than remain ignorant, to reach outward rather than turn inward. Space exploration embodies these values. It's fundamentally about curiosity, about wanting to know what's over the next hill, across the next ocean, beyond the next star. That curiosity is one of the best parts of being human. It's led us to every discovery, every innovation, every advancement in understanding, and it's not satisfied. There's always more to discover, more to understand, more to explore. The cosmic horizon might limit how far we can physically travel, but it doesn't limit how far we can see, how much we can learn, or how deeply we can understand. So here's what I want you to take away from this entire exploration. Yes, there are absolute limits to human travel through space. Light speed is a hard boundary enforced by the structure of space-time itself. Cosmic expansion creates an event horizon beyond which galaxies are forever unreachable. These limits are real, fundamental, and based on our best understanding of physics. But within those limits, there's still an incomprehensibly vast frontier, hundreds of billions of galaxies, trillions of stars, countless worlds to explore and understand. We're at the very beginning of that exploration. We've taken our first steps off our homeworld. We've sent robots to nearby planets and probes to the edge of our solar system and beyond. We've looked through telescopes at the most distant galaxies, gathering photons that have been traveling for billions of years. Every generation adds to this body of knowledge, pushing the boundaries of what we know a little bit further. And that process, that gradual expansion of understanding, is itself a form of traveling through space. We reach distant galaxies not with spacecraft, but with instruments and intelligence. The future of space exploration will be a combination of physical presence and remote observation, humans and robots working together, near-term goals like returning to the Moon and reaching Mars, medium-term goals like exploring the outer solar system and searching for life on icy moons, long-term goals like sending probes to nearby stars, and eventually perhaps establishing interstellar colonies. All of this is possible within the framework of known physics. It's difficult, expensive, and requires sustained commitment across generations, but it's possible. And even if we never leave our solar system, even if interstellar travel proves too difficult and humanity remains forever bound to the sun's gravitational embrace, we can still participate in the cosmic story. Through telescopes, through mathematics, through thought and imagination. We can observe distant galaxies, study their properties, understand their evolution. We can map the large-scale structure of the universe. We can test our theories against observation and refine our understanding. This is exploration through knowledge rather than presence. And it's just as valid, just as meaningful. The absolute limit of human travel through space is the cosmic event horizon, currently about 16.5 billion light-years away and shrinking over time as the universe expands. 95% of galaxies in the observable universe are already beyond that boundary, forever unreachable no matter how fast we travel. The remaining 5%, roughly 100 billion galaxies, constitute the reachable universe. That's our cosmic neighborhood. That's the portion of the universe we can potentially explore, colonize, and come to know intimately over the coming millions and billions of years. It's a finite but vast region, more than any single civilization could fully explore, more than enough to keep us learning, discovering, and marveling for the entire future of our species. The universe has given us a large enough playground, not infinite, but large enough. And within that playground, we're free to explore, to question, to understand, to create, and to become whatever we choose to become. That's the ultimate answer to the question we started with. How far can humans travel through space? The answer is far enough. Far enough to spread across thousands or millions of worlds, far enough to ensure our long-term survival, far enough to encounter wonders we can't yet imagine, but not infinitely far, not to every galaxy, not to every corner of the observable universe. Some places will forever remain beyond our reach, visible but untouchable, knowable but unreachable, and maybe that's appropriate. Maybe the universe is supposed to retain some mystery, some territory beyond our grasp. Maybe the cosmic horizon is nature's way of reminding us that we're not the center of everything, that we're part of something much larger than ourselves, and that humility in the face of the infinite is a virtue worth cultivating. So as we look up at the night sky, at the countless stars scattered across the darkness, we should feel both small and significant. Small because the universe is vast beyond comprehension, and we're tiny specks within it. Significant because we're the parts of the universe that have woken up, that can look back at the stars and understand what they are, where they came from, and what they mean. We're how the universe knows itself. We're consciousness emerging from matter. We're stardust pondering stars. And that ultimately is the most important journey. Not the journey outward through space, but the inward journey of understanding. The journey from ignorance to knowledge, from isolation to connection, from seeing ourselves as separate from the cosmos to recognizing that we're integral parts of it. Space exploration, whether physical or intellectual, is a tool for that deeper journey. It expands our minds even as it extends our reach. The limits are real, but so are the possibilities. And in the balance between limitation and possibility, between what we can and cannot do, we find meaning, purpose, and the motivation to keep exploring, keep learning, keep reaching for the stars, even knowing we'll never touch them all. Thank you for taking this journey with me through the absolute limits of human space travel. I hope it's given you a new perspective on our place in the cosmos, on what's possible and what isn't, and on why the journey of exploration matters even when the destination is unreachable. The universe is vast, mysterious, and wonderful, and we're lucky to be part of it, if only for a brief moment in cosmic time. Keep looking up, keep asking questions, keep wondering. That's how we honor the gift of consciousness and the extraordinary universe that created us. If you made this far, I am sure you will love this other video at the left side of the screen. This is why we are stuck in the solar system forever. Learn why even our fastest spacecraft like Voyager and Parker Solar Probe barely scratch the surface of interstellar space, and why every proposed technology, fusion rockets, antimatter engines, warp drives and generation ships, runs into the same impossible physics and engineering challenges.